All right. Hello, everyone. Let's see who's here. All right. It says there's 10 people here, 11, 12. Okay. All right. Good. So, hi, everyone. I hope all of you had a good weekend. Welcome back to the course. So today, I want to continue with LR parsing, basically continue where we left off last Wednesday. And then I'll talk a little bit about the assignment as well, and then we'll continue with parsing. Okay, so just a recap of where we were on Wednesday. So we looked at bottom-up parsing and specifically an LR0 parser. And so I had an example LR0 grammar here. And the idea of bottom-up parsing is that we're constructing the derivation in reverse. So we start with the input string, which in my example was a plus a, augmented with the $sign. And at each step of the parser, we're applying one of these production rules in reverse. So for example, turning the a into an e. And so we build the derivation in reverse. And sort of the hope is that eventually we will reach the start symbol of the grammar. All right. And so this was the overall algorithm. We were using a stack to hold the current step in the derivation. And there were two main operations, reducing and shifting. And reducing is where you pop gamma and push a. So that's where you apply one of these rules in reverse. And shifting is where you take something from the rest of the input. So you take a symbol a from the rest of the input, and you push it onto the stack. So now it becomes no longer part of the rest of the input, but it's on the stack so that then in the next iteration of the outer loop, we can try to use it to reduce. Okay, and the one invariant that we had was that since we were starting from the input string, it's always the case that whatever you have on the stack plus the rest of the input derives the input string. But what we're kind of less sure about is that our current step in the derivation, so whatever you have, like say the e plus a, that there's still a hope of eventually reaching the start symbol of the grammar. Okay, and to ensure that there is always this hope, we defined the idea of viable prefixes. So viable prefixes are prefixes of sentential forms. So prefixes of things that you can derive from the start symbol. And then we want to maintain this invariant that the stack is always a viable prefix. All right, and then we talked about, how do we know whether the stack is a viable prefix? And, it was hard because the set of viable prefixes, you would need a parser to answer that question. And so you would need a parser to make a parser. But it turns out that the viable prefixes that actually ever show up as stacks are a regular language. And so we built this NFA for that regular language, and it's here behind me. This is the NFA for this example grammar. So we're going to use this NFA to decide whether we have a viable prefix or not, to decide whether it makes sense to reduce, right? Whether that would get us out of a viable prefix, and to decide when to reject, when the parser should give up and give an error. Sorry, I erased this part. This said error here, right? So if we're pushing a onto the stack, then the new stack will be stack plus a. And so if that's no longer a viable prefix, then we give up hope and we give a parsing error. Okay, and so I talked a lot about building this NFA last time, so I won't go into too much more detail there, except for there was this thing with these epsilon transitions that Yeah, no. Okay, so I've already erased the ones that I wanted to erase. Okay, so there were these extra epsilon transitions from these states where the dot is at the end back to other states, and if we needed to have those, then we would have to keep adding states to the NFA, and it would become infinite. And sort of the key was that we don't need to ever follow those epsilon transitions, and therefore the NFA stays finite. And basically, there were these epsilon transitions that you take whenever you're in a state where the dot is before a non-terminal symbol. So like here there's a dot E, and here there's dot E. So you build these epsilon transitions, and if we never need those backward-facing epsilon transitions, then these epsilon transitions can just loop back, like this one can loop back to this state. Otherwise, we would have had to create a whole new copy of this state and all the other states reachable from it. And similarly, for this epsilon transition, it can just go back to the existing state. If we had these epsilon transitions going back, then we would have to have one from here going back here, and one from the copy of this state going here, where the dot has jumped over the E. And so then this whole thing would have to be copied. Okay, so I mean, that's a recap of the last lecture. Are there questions at this point, before I move on? Okay, so think about questions. I'm going to start moving on, and if questions pop up, then we'll see. All right. So one thing I want to look at is this reduce here, and I have this important thing to say that I had on the board last time, but I'm going to write it again. So the question is, when do we reduce? Okay, and so we call reduce on the stack. So here I'm going to say that alpha is the stack, right? So here we're going to call reduce on the stack. And so, when do we want to reduce the stack? Well, we want to reduce it if after doing this reduction, the stack would still be a viable prefix. Okay, so this is going to be a set, and let me make some more space here. So this set is going to contain A goes to gamma if, first of all, gamma is at the top of the stack, so A ends with gamma. So I'm going to write that as there exists a beta such that alpha is beta gamma. So I can, split up the stack into something plus gamma, because we're going to pop gamma off the stack. And beta A is a viable prefix. Okay. All right. So that's what we had before. So the idea is that if I go ahead with this reduction, then after the reduction, the stack is going to be beta A, and I want that to be a viable prefix. All right. And so now the question is, how do I use this NFA to decide when to reduce, right? So the NFA accepts viable prefixes, but what does that tell me about beta A? So where is beta A in the NFA? Okay, so I'm running the NFA not on beta A, but I'm running it on beta gamma, right? I'm running it on the stack. And so I know the stack is a viable prefix. So this is the NFA is going to go to some accepting state, and all the states are accepting states. So it's going to end up somewhere. It could even end up in multiple states. But when is beta A a viable prefix? Okay. And well, the answer is that beta A is a viable prefix if running the NFA on beta gamma leads me to one of these states that has a dot at the end. Okay, but it's not totally obvious why that is the case. So I'm gonna say here, if running the NFA on alpha, and I'll do the squiggly arrow just to say that the NFA ends up in a state that has A goes to gamma with a dot at the end, and I'll draw it as a state here. Okay, now why is that the time when beta A is a viable prefix, right? Well, so you have to ask yourself, why is so I run on the stack and I end up, let's say, here. Okay, so what you have to ask yourself is, why is this state in the NFA in the first place? And well, the state is there because this other state was here where the dot was before the A. And then part of the rule of building this NFA is that whenever you have a dot before a symbol, you put an edge where the dot jumps over the symbol, right? And then similarly here, we had a dot at the beginning and a bunch of states, all the way to here where the dot is at the end. Okay, so this state here with the dot at the end is there because, there were these other states before it. And it really started here where the dot was at the beginning. So why was this state here with the dot at the beginning? Or this other state with the dot at the beginning? Where did they come from? Well, they came from the fact that I had a dot before a non-terminal symbol, and I took an epsilon transition to a state where that non-terminal symbol is being expanded by some production rule. Okay, so you can like memorize this fact that you reduce when the dot is at the end, but the reason goes back, long before this state. You go back and then you go back here to where there was a dot before a non-terminal symbol, and we took an epsilon transition, and then we went and jumped the dot over the right-hand side of that production rule. Okay, so if this is here because of this, and this is here because of this, why is beta A going to be a viable prefix? Well, let's look at, what is beta? Well, beta is the thing that comes before gamma on the stack. And what's gamma? Well, gamma is the symbols on these sideways transitions, right? So in this case, the gamma is the A. In this case, the gamma is E plus A. So that's gamma. So beta is what comes before. So beta is the string that takes the NFA to this state where the dot was before the non-terminal symbol. Okay, and in our case, that non-terminal symbol is A. So beta is what takes you to that state that has the dot before the A. And now maybe it's getting clearer, right? Now you see why beta A should be a viable prefix, because beta got us to a state where the dot was before A, and if the dot is before something, then there's another transition on that something. And so we take beta to here, and then we take that non-terminal symbol A to here, and it's still an accepting state. So beta A is a viable prefix. Okay, so once again, you can kind of memorize that when the dot is at the end, that's when you reduce by that rule. But why that makes sense is actually pretty tricky, because what the string that takes you to that state with the dot at the end is beta gamma, but the string that you actually care about when you're deciding whether to reduce is beta A. Okay, so I mean, that was important, and I explained it a lot. Did I explain it enough? Are there questions? And even if there isn't a question, can I get at least one person to post a comment just to make sure everyone's here and everyone can hear me? And now everyone's going to post and it's going to explode, but or not. Okay, so oh yes, all right, we got a comment. All right, so there is someone here. I mean, it says there's people here, but good. All right, thank you. Okay, there's 2 people, 3 people. Yay! All right. Okay, there's lots of people. Great. Okay. All right, and so okay, you're here. That's great. Did you get that right? Did you understand that? Are there questions about this? Okay, so we want to reduce if our NFA takes us to one of these states, and we want to. All right, so okay, so we have this NFA, and remember that an NFA can be in lots of states at the same time. Okay, and so let's so before we're going to run the parsing algorithm, let's do our conversion to a DFA so that the parser doesn't have to keep track of multiple states that it's in. So, all right, I'm going to say convert NFA to DFA. All right, and now if I run the DFA, a state of the DFA corresponds to a set of states of the NFA that could ever appear simultaneously, right? So if on a given stack, I can, I run the NFA and I get to, let's say, this state and this state, right? So the NFA can be in multiple states at the same time. Then those 2 states will appear in the same state of the DFA. But, I have to be careful here because, if the NFA says, oh, if you reduce by this production rule, you'll still have a viable prefix, and you reduce by this production rule, you'll still have a viable prefix, then that's bad because then I don't know which production rule is the right one. And in fact, both could be the right one depending on what the rest of the input is. Or even for a single input, both could be right if the grammar is ambiguous, right? There could be 2 different derivations, one that uses this rule, one that uses this rule. Okay, so if my NFA can ever reach this state and this state at the same time, or any 2 states that have the dot at the end, that's bad because then my NFA doesn't tell me what to do. All right, it says, oh, try this or try this. And all right, which one do I do? I don't know, right? So, and how do we know whether an NFA can ever end up in 2 specific states at the same time? Well, we convert it to a DFA, and if those states, those 2 NFA states ever show up in the same DFA state, then it's possible for the NFA to end up in those states at the same time. All right. So, I'm going to convert my NFA to a DFA. So, and then if a state contains 2 different productions, right? So A goes to gamma, and let's say B goes to delta. Then that's a reduce conflict. So it's called a reduce conflict. Okay, and that means if the parser were to reach that state, it wouldn't know what to do. And so we're going to say that the grammar is not LR0 if it has such a conflict. If we can't, unambiguously tell the parser. So if there is an input that drives the stack to a particular contents of the stack that would make the NFA be in both of these at the same time. Okay, and we'll, soon enough we'll see examples of grammars that have such a conflict. Okay, what else can happen? Well, the other thing that can happen is here, I am trying to decide, I'm trying to decide, should I reduce or should I not reduce, right? And so one problem is that, maybe reducing by multiple production rules still gives me a viable prefix. But, what if the right thing is to not reduce, right? Or what if it just so happens that, yes, reducing will give me a viable prefix, but not reducing, would have also been fine, right? So getting out of this while loop would have also been fine. Okay, so that is also an ambiguity and also a choice left up to the algorithm. And so we don't want that either, right? And so specifically, we only want to reduce here in cases where this would fail immediately, right? Where pushing another symbol from the alphabet in this particular state would get us out of the set of viable prefix, would give us no longer, no more hope of reaching the start symbol of the grammar. Okay, so, how do we know whether it's okay to not reduce? Or in other words, if we reduce and then we push something, will we still have a viable prefix? Well, okay, so, if I'm in a state, let's say I'm in this state, or, pick a state, any state, and my stack takes me to this state, and then I push something, and, I'm not looking at what that something is. There's something that I push. Is there a hope that I have a viable prefix? Well, yes, there is a hope, because if that something that I'm going to push happens to be A, then, pushing that on the stack is going to make the stack plus A take me here. And so then there is going to be hope. All right. So to flip that around, if I'm in a state like this, now there's no hope, right? If I'm in a state like this and the stack gets one more symbol on it, then out of this state, I would have to go to some other state, but there are no transitions outwards. So if I'm in a state like this, it's safe to reduce. But now, again, it's an NFA, so it can be in two different states at once. And so, if it's in a state like this, then there's a hope that not reducing is the right answer. And if it's also at the same time in a state like this, then there's a hope that reducing is the right answer. And then again, the algorithm would have to try both, and it would have to backtrack, and that's not what we want. All right. So, similarly, I'm going to summarize this and say, if a state contains really a NFA state with a dot at the end and an NFA state with a dot not at the end. So dot at the end, and B goes to, I'm going to write it as alpha dot x beta, then we're going to call that a shift reduce conflict. All right. Okay, so if there's a state with a dot at the end and a state with a dot not at the end, if that's ever possible to reach those two states simultaneously in the NFA, then the algorithm, it could be that reducing is the right answer. It could be that not reducing is the right answer. And we never want to, be in that position of not knowing which is the right answer. Okay, I think I gave it away that, this is an LR0 grammar, and so there shouldn't be any conflicts. But let's confirm that and build the DFA for this grammar. And I'm just worried about how it's going to fit. All right, I think I can fit it on here. Okay. So once again, so I'm not getting any questions. So hopefully that means everybody gets it. But feel free to ask if there are questions. Okay, so converting this NFA to a DFA. So we start with the start state. We take the epsilon closure. We follow epsilons. And so our initial DFA state is going to have S goes to dot E $. It's going to take an epsilon transition to E goes to dot A. And another epsilon transition to E goes to dot E plus A. Okay, and that's the start state of the DFA. Okay, and I think I said last time that I'm going to stop drawing double boundaries, but all of the nodes are accepting nodes in all the NFAs and DFAs we're going to see from now on. So this is an accepting state. Okay, and now, okay, how did we do this? This is, thinking back to scanning, right? How do we build a DFA out of the NFA? So if I'm in this state and, let's say I see a capital E right here, then, where am I going to go? Well, I'm going to go to the state S goes to E dot $. And again, I would have to do an epsilon closure, but there are no epsilon transitions there, so I'm good. And but I'm also in the state E goes to dot E plus A. So if I see an E there, I will go to E goes to E dot plus A. So I'm in that state as well. All right, so A. Okay, and so this is my next DFA state. By the way, I guess as I'm doing this, I should be checking that there's no conflicts. So, do I ever have a state with a dot at the end and another dot at the end, or a dot at the end and a dot in the middle? And so far, there's no dots at the end, so I'm safe from any conflicts. Okay, if I'm in that start state, the other symbol I might see is an A. And so if I see an A, and I'm here, I go nowhere. I'm here, I go to E goes to A dot. And if I'm here, I see an A, I go nowhere. So I have a state here. And now if I look at this state, where can I go? Well, if I see a $, right, there's this transition here that takes me to S goes to E $ dot. And I can also, if I'm in this state, I could be here where there's a plus. So a plus would take me to E goes to E plus dot A. Okay, and then finally from here, I might see an A and go to E plus A dot. Okay, so I mean, this is a good exercise to review the DFA, NFA to DFA conversion. But here's my DFA, and if I check everything, there's no conflicts, right? So the only states that have a dot at the end, don't have anything else at the end. So I'm happy with this DFA. It's always going to tell this algorithm what to do. Okay. All right. So my screensaver froze. Okay, I'm back. Okay, so there's no conflict. So why do we, why do I care so much about conflicts? I want to talk about the assignment a little bit. All right, so for the assignment, sorry, I'll stand over. Well, all right, whatever. So for the assignment, I am giving you code that builds this NFA and converts it to a DFA. It's on the course website. It's called JLawler, and it's you find it on the course website. This is code that's written in Java. It takes a grammar as input, and it will build this NFA and then the DFA for you, and it will output it. And there's a documentation there about the format that DFA is in. Okay, so you don't have to implement this algorithm yourself of building this NFA. Feel free to do so. I think it's a good exercise, but I think it's a bit too much work for this course to force everybody to do it and debug it and get it right. So that's why I'm giving you that algorithm. But you still need to, I'm giving you that implementation. But you still need to get a solid understanding of those algorithms. And typically the way that you will understand them is as you are designing your grammar, chances are you will have ambiguities in your grammar or things that are not LR0 or not LR1. My advice is to start with the rules one at a time for individual features, so it doesn't get too big before you start seeing conflicts. But then when you see a conflict, well, what does a conflict mean? Well, this is what it means, and this is where you have to go back. Is it back? Okay. How do we? What can I do here? Well, I can reconnect my internet. It's back now. Okay. Back. All right. Okay. Okay. I don't know if that was because I did anything, but okay. So how much did I miss? When you guys started saying the stream is dead, was it like a minute or was it like 10 seconds or? So I was talking about the assignment and how the way that you're going to see to learn how all this works is right. Okay. So if you see a conflict, that suggests there's something in your grammar where reducing is the right thing to do or shifting is the right thing to do. And so at that point, that's where you're going to need to look at your grammar and think about, what input would cause the stack to get into the state that the tool reports for you. And then when you're in that state, if you had seen that input, in what cases would you have additional input that would mean that reducing is the right answer, that applying that production rule in reverse is the right answer, and in what cases would you have input where it means that pushing more stuff onto the stack is the right answer, and that after you push more stuff on the stack, then you're going to end up reducing by some other rule. Okay, so the tool the implementation that I give you, when it sees a conflict, it tells you about the DFA state where the conflict appeared. So, so for example, it will tell you that, maybe this DFA state had a conflict. I mean, it doesn't because, but anyway, it'll output all the NFA states in that DFA state. So if there's one with a dot at the end, so you're thinking about reducing by that rule, and let's say one with a dot not at the end, so you're thinking about, okay, if that A is the next thing in the input, then maybe shifting that A and reducing by a different rule later is that's a better answer, right? And so you need to think about, okay, is that an ambiguity, or and if it is, well, then you need to fix your grammar so that your grammar forces one or the other. So I guess in terms of advice, don't underestimate the effort needed to design the grammar, right? I mean, yes, implementing all this would have been effort, but I gave you that implementation, but you're going to understand that implementation, or at least understand the algorithms in that implementation in the process of playing around with the grammar and getting that experience. Okay, so stop me if there's questions, and hopefully the internet is working. The other thing that you do need to implement is this part, right? So this is the part that is the actual parser. So I'm not giving you that. So that you implement in whatever programming language you are using, and it needs to answer this reduce question and this reject question, right? So it's running the NFA on the stack here, the stack plus A here, and here, if the NFA or the DFA rejects that input, then you give an error. Here, you're trying to see, is the DFA ending up in a state with a dot at the end? Okay, so this part you do have to implement yourselves. Okay. So, questions? No. All right. Okay. All right. So I want to do one more optimization to this algorithm that actually runs the DFA, and let's see. Well, maybe before that, let's quickly do an example of parsing a particular input stream. Okay, and I guess for that I can erase the the NFA, and we can have the DFA. All right, so I got rid of the NFA. So okay, we had the example before of A plus A, and I'm going to use this notation where so the current step in my derivation is represented by the contents of the stack and the unseen input. So the rest of the input. Okay, and so at the very beginning, the unseen input is all of the input, and the stack is empty. So at the very beginning, the stack is empty. The unseen input is A plus A. Oops. Sorry. Okay. I can't write for some reason. So the unseen input is A plus A $, right? So this is the same example we tried to parse before. And okay, and so the algorithm says, should I reduce? Well, so I run the DFA on the stack, and it gets me to this state. And this is a state where there's no dots at the end, so I'm supposed to shift. So I get out of this while loop, I go down here, and I push A onto the stack. So now my stack is A, and the rest of my input is plus A $sign. Okay, and I go around this other loop, and I've processed the A, and the rest of my input is now plus a $sign, and so I do this again, right? I run the DFA on the stack. So now the stack is A, so I'm here, and the dot is at the end, so it says reduce by this rule, and reducing means pop, well, gamma, but gamma is little a here, and push big A, which is big E here. So I'm going to pop the A off the stack and push E in its place, and the rest of the input stays the same. And then I go and run the DFA again. So I start at the start state, I go E, and I'm in this state. The dots are in the middle, so that means push. So then I push E, I take, it means shift. So I take the plus from the input, I push it onto the stack, and I go around the loop again, and now the input is shorter, so the input is just a $sign. Okay, and now I run the DFA on the stack again. So E plus, it takes me to this state. That's a shift state. So I shift the A onto the stack. Only the $sign is left. And I go and run the DFA again. Okay, so I go DFA. So E plus A, and now I'm in this state, and that's a reduced state. It's got the dot at the end. So I reduce, I pop E plus A off, I push E in its place, and then I have the $sign, and then I go and run the DFA again. And I go, I go E, and it's here, and that's a shift state. So I push the $sign on the stack, and now I'm done because I've got E $sign. I've pushed the $sign onto the stack down here, and then I got to the end of this loop, and then we talked about this in the last lecture. If you want, you can add an extra reduction step to turn the E $sign into the start symbol. But that last step is sort of optional. You might just want the tree to be rooted at E and ignore that $sign, right? Because that's just a marker for the end of the input. Okay, so one, are there any questions? And two, is somebody there just to make sure that things haven't frozen again? So somebody say something. Please. Somebody comment. Yes. All right. Okay. Great. Okay. So, I mean, that's an example of it running. So if there's questions about, that example, how does that work? Ask those questions. But one thing that was annoying about running this is, I kept following the same path over and over again in the DFA, right? I had E plus A, and each time I would go to the beginning and I would go, all the way through, mostly the same path, but, maybe just adding an extra symbol to the end of the stack. All right. So, that's, it's fine. It's correct. It will parse, but it's a little bit inefficient. If the stack gets really long, then for each symbol that you look at, or for each action that you do, you're going to be running this DFA. Okay, you're going to be running it over and over again on a potentially long stack. So an optimization that you can implement is, well, we're going to have a second stack. Whoops, second stack. Okay, called a symbol stack. No, called a state stack. Sorry. So the symbol stack is the stack with the symbols on it, the one we already have. So we're going to call this a state stack. And the idea is that the state stack keeps track of the DFA state that you end up in after running the DFA on the symbol stack. Okay, so we're going to maintain this invariant running the DFA on symbol stack ends in the state on top of a state stack. Okay, so we have this second stack, and it just keeps track of where the DFA would end up if I was to run the DFA on the symbols in the symbol stack. All right, and so the idea is that I can maintain these two stacks together, sort of in sync. So every time I push on one stack, I push on the other stack as well. And if I pop off one stack, I pop the same number of symbols or the same number of entries from the other stack. And so that way, you know, let's say my stack is E plus, and now I'm pushing E plus A on the stack, and I want to know where the DFA goes on E plus A. Well, then I don't have to go all the way to the start state and go through the DFA E plus A, because, you know, before I did the push onto the symbol stack was E plus, and I just pushed an A, and the state stack, you know, the top of that stack told me, oh, I'm in this state. And so if I just push an additional A on top of the symbol stack, that means only taking one extra transition on this A in the DFA. So I can take that transition and push this state onto the state stack. So as long as I keep the stacks in sync, so I always push on one at the same time as pushing the other and pop off one whenever I pop off the other, then the stacks can keep track of where the DFA would end up on the if you were to run it on the symbol stack. And you know, each time I push a new symbol on that symbol stack, I need to only follow one transition in the DFA to find that new state and push that onto the state stack. Okay, and then similarly, whenever I pop, right, so let's say here, I'm going to pop E plus A off the state stack, off the symbol stack, and then I'm going to push E in its place. So when I pop E plus A, well, then I want to pop 3 states off the state stack, right? So the state stack is going to have this, because what states do I go to on E plus A? If I pop 3, then the top of that state stack is going to be the start state. And now if I push E, I'm going from the start state on an E, and I can push that back onto the state stack. Okay, so I keep these in sync, and this avoids having to rerun the DFA every time. But in terms of correctness, it doesn't change anything, right? It would be perfectly fine. And the theory, you know, the theory says run the DFA on the stack and rerun it on the stack each time. This is just remembering where you would end up on a prefix of that stack. Okay, and that just makes things faster. Okay, so questions. All right. Okay, so the algorithm that we've had so far is an LR0 parser, and we'll look at why in just a moment. And and so the J Lawler tool that I give you, it can build LR0 parsers, but I wouldn't recommend that for the JUICE grammar for your project, because an LR0 parser is going to have lots of conflicts on practical grammars. Okay, so on the other hand, that tool can also build LR1 parsers, and those have much fewer conflicts. And so my recommendation for the assignment is do the LR1, right? Build an LR1 parser and try to get your grammar to be LR1. If it's LR0, it's also LR1, but not the other way around. So the LR1 is going to be the easiest grammar to build. And now, okay, so what's an example, right, or what's the difference between an LR0 grammar and an LR1 grammar? Okay, well, and I said with LR0, we're going to have lots of conflicts. So let's see an example of that. All right. So I'm going to... I maybe don't want to erase. I was going to erase that, but maybe that's a bad idea. All right, I don't want that. So, all right, let's put the grammar right here. All right, so here's a grammar. And I'll augment it right away. So S goes to E $, and E goes to A plus E, and E goes to A. Okay, so this is a grammar that's similar to the one we had before. Here's the one we had before if you ignore the dots. So we had the start rule, we had the A, and then we had this one. So the only difference is that this is a grammar that's right associative, right? The E is on the right of the plus, whereas here it was on the left of the plus. So, you might have constructs in your grammar that should be parsed right associatively. And so you might have a grammar like this. Probably not for addition, but yeah. So if I, let's say this is my grammar. And so if I try to build the DFA for it, how's it going to look? And, okay, so here I should go through all the steps and build the NFA and then do the NFA to DFA conversion. I'm going to invite you to do that yourselves as an exercise. But I'm just going to, quickly kind of do all those steps in my head. You might, at this point for a little grammar like this, you might be able to do it in your head as well. So the NFA would have a start state where you have the start symbol, you have this start, the augmenting production rule. So S goes to .E $. So that would be, what we would have as the start state of the NFA. And that start state has a dot before the E, which means we would have epsilon transitions to start states of these. So we would have an epsilon transition to E goes to dot A plus E. Okay, and also an epsilon transition to E goes to dot A. And, when I convert that NFA to a DFA, the epsilon closure is going to include those three NFA states in a single DFA state, right? So I'm kind of doing a lot here all at once. Once again, feel free to do the exercise of building the DFA, building the NFA and then converting it to a DFA. Okay, and so here, I've got a dot with an E and a dot with an A, and so there would be outgoing transitions, let's say one on an A and an outgoing, an outgoing transition on an E. I'm going to ignore that E1. You can, again, as an exercise, you can complete this. But on the A, what would happen? Well, from these states, it's the dot jumps over the A, right? So from this state on an A, the NFA would go to a state that looks like E goes to A dot plus E. And on this state, we would jump the dot over the A, and we would go to a state that has E goes to A dot. Okay, and now, there's going to be more things out here. So specifically, there's going to be a transition out on the plus, but, there's going to be more stuff there. Okay, so I haven't built the whole DFA yet. I probably should, and I'll let you build the whole DFA as an exercise for yourselves. But to demonstrate the issue, I don't need the rest of the DFA. I have a conflict here, right? I have a shift-reduce conflict because I have a state where the dot is at the end and another state where the dot is not at the end, okay? So what happens? So what does this conflict correspond to in the parser? Well, in the parser, so how do I get to this state? Well, one way I get to it is if the input is A. And so if the stack has an A on it, do I shift or do I reduce? Well, I don't know. So if the input, if I've seen the input A and I've pushed it onto the stack, so from this state I did a shift. So I've pushed the input A onto the stack. Is it a good idea to shift? Is it a good idea to reduce? Well, it depends on what the input is. The input could be, so let's see, if the input is, let's say, a $, right? So if my entire input is just A, then I want to shift, right? Because my shift, so my stack is A and the rest of the input is $. I'll shift and then I'll be done with the input. And I'll be done my parse and I'll accept the string. On the other hand, like let's say the input is A plus a $. Wait, did I? Oops. Okay, I should read my notes before I. Yeah, and I messed it up. Okay, let me rewind a bit here. Okay. All right. So the part that is still correct is that the input could be a $, or the input could be A plus a $, right? Those are both valid inputs. They're both generated by this grammar. So either of these could happen. In both of these cases, my stack is going to be A, right? I'm going to be in this state. It says shift, and I'm going to push the A on the stack. So now my stack is A. So the DFA runs on the A, and it leads me to this state. And okay, when is it a good idea to reduce? Well, in this case, the right answer is to reduce by the rule E goes to A, because that will turn the A into E $, and then my stack is going to be E. The rest of the input is going to be $, and I'm going to be done my parse, right? The start symbol derives E $, which derives A $. Okay, so here I want to reduce. If the input is A plus A, and my stack has A on it, then the rest of the input is plus. And what I need to do is I need to keep shifting until I have A plus A on the stack. And then once I have A plus A on the stack, I'm going to reduce by the last rule to change the A to an E. And then I'm going to reduce by the second rule to replace the A plus E that's now in the stack with an E, and then I'll have E $, and I'll be done. So if the input is this one, then the right answer is to shift. Okay, and let me just kind of draw a line here. On the left of the line is what's on the stack. On the right of the line is the unseen input that I haven't looked at yet. And my DFA only looks at the stack, right? So the DFA, it just sees A, and it doesn't know whether I'm in this case or in this case. So, okay, so it can't make a decision, right? It doesn't know what to do. But if you could look at one more symbol of the input, then you could tell these two inputs apart, right? You look at one more symbol, it's either a $, or a plus, and then you'll be able to tell them apart. Okay, so this is the LR0 parsing algorithm. And now I'm going to give you the LR1 parsing algorithm. And I want to write LR1 somewhere. All right, let's do it here. So LR, and then in red I'll put 1. Okay, so we're gonna use a different algorithm, but the LR1 algorithm is almost identical to the LR0 algorithm. YouTube hates me. Okay. All right. So it's almost identical. The only difference is my reduce function here. I'm going to give reduce a bit of extra information, and I'm going to tell it that after the stack, I have the symbol little a. Okay, that's that next symbol from the grammar, from the input that you have. So now the NFA or the DFA that has to make the decision, it has the stack A, but it also knows whether there's a $sign after it or whether there is a plus after it. Okay, and how? So how is this going to work? Well, or when should the NFA or the DFA say to reduce or to shift? Well, okay. I have this, right? So this was, when do I want to reduce when the stack is alpha, right? And I want to reduce by that production rule. If after I reduce, my stack would be beta A, and that would still be a viable prefix. So now, if reduce has this extra information about the next input symbol A, how can it use that extra information, right? So, what's going to happen? So the stack is still beta gamma, right? I still want to pop gamma off if gamma is at the top of the stack. But what needs to be a viable prefix, after I reduce? Well, okay, so after I do the reduction, beta A is going to be a viable prefix. But what I want is my sentential form, right? My entire, let's say the stack plus the whole rest of the input. I want that to be possibly derivable from the start symbol. So I want really any prefix of the stack plus the rest of the input to be a viable prefix. So the way I'm going to modify this here is I'm going to want beta AA is a viable prefix. Okay. So, okay, so here's how this is all the modifications that I have to make to turn the LR0 parser into an LR1 parser. So I have to tell reduce not only the stat, but the next input symbol that's coming. And reduce is going to try to determine not only whether beta A is a viable prefix, but whether beta AA is a viable prefix. Okay, and so let's just look at the example here, right? So the decision I'm trying to make is, should I reduce the A to an E? And so in this case, my stack plus input symbol is going to be E $, and that is a prefix of a sentential form, right? I can derive E $, from the start symbol. In this case, if I apply the rule, replace the A with E, my beta AA here is going to be E plus, and does E plus ever appear in something that you can derive from the start symbol? In this case, no, it doesn't. Okay. So, I mean, all right. So, trivial modification, right, to the algorithm. We just provide reduce with more information, and reduce now looks at whether beta AA is a viable prefix instead of just beta A. All right, and that's all I need to do. But now, I mean, it's a tiny modification, but I need to go back to the question, how do I know whether beta AA is a viable prefix? Okay, and before, when we were just looking at beta A, I had that NFA, and I was able to build the NFA to deal with all the betas that might ever come up. And there was this special case where no, I can't build an NFA for all viable prefixes, but I can build one for ones that come up as stacks. So for ones that come up as beta gamma, to tell me whether beta A is a viable prefix. But that NFA doesn't work for this slightly changed question of whether beta A little a is a viable prefix. Okay, so all right, so what am I going to do, right? So to really answer this question, those epsilon transitions that I said, oh, we don't need those. Well, we would need those again, and our NFA would get infinite, and everything would fall apart. Okay, so we're going to do two things. We're going to try and do two things. All right, this one I can erase. Okay, so remember, we're trying to answer this question. Is beta AA a viable prefix? And so let's try two different ways of doing it. So we're going to have option one. So option one, and then we'll have option two. And all right, I mean, option two is going to be, build a better DFA. Okay, so we're gonna, go back and redo all the stuff we did, and build an NFA and look at which epsilon transitions we can remove, and and this is going to be complicated, right? And it's going to be a big DFA and so on. But this is called the LR1 algorithm, and it's a lot of work, and we will do it, but not today. Option one, can we kind of answer this question sort of more easily with the existing DFA? Okay, and specifically, I'm going to look at the follow set. Okay, so remember the follow set from the LL parser. Okay, so if A is not in the follow set of A, of big A, right? Yeah, what does the follow set say? Well, the follow set tells us, is there any sentential form that has big A, little a in it, right? That has little a following big A. So if there is no sentential form with big A, little a in it, is beta AA a viable prefix? No, right? So if A is not in the follow set of A, then no viable prefix can ever have big A, little a in it. And so therefore, beta AA is not a viable prefix. So then beta AA not a viable prefix. Okay, so I want to do so option one is called an SLR1 parser. The S sometimes it stands for simple LR1, but the idea is if beta AA might be a viable prefix if beta A is a viable prefix and little a is in the follow set of big A. Okay, so so with the SLR1 parser, we're not going to answer this question exactly, right? Is beta AA a viable prefix? But we're going to approximate it, and we're going to say, we're going to ask if beta AA is going to be a viable prefix, then beta A has to also be a viable prefix because beta A is a prefix of beta AA, right? So if this is the prefix of a sentential form, then so is this shorter one, and little a has to be in the follow set of A, of big A. All right, and so the SLR parser is going to approximate this question this way, and okay, so how do we answer this question? Is beta A a viable prefix? Well, we know how to answer that question. We have a DFA that answers that question from the LR0 parser, right? So, this is answered by the LR0 DFA. Okay, so we can answer that question. Is A in the follow set of A? Well, let's, we build the follow sets beforehand, just like we did for the LL parser. And, so we can have a table with answers to that question as well. And, okay, and this is actually going to be enough to resolve the conflict for this grammar. So I should say that this grammar here is an SLR1 grammar. Okay, so it's not, you can't parse it with an LR0 parser, but you are going to be able to parse it with a SLR1 parser, which means you can still use the same DFA, you just need the follow sets. And so, you know, what's in the follow sets, or you know, let's compute the follow sets for this grammar. So, you know, what's in the follow set of S? So how can S ever appear in a sentential form? Well, S only ever appears at the beginning of a derivation. After that, it turns to E $, and then there's no more S's anymore. So no sentential forms ever have anything after an S. And the follow set of E is, well, okay, so I can have a $sign after an E, right? So I have a sentential form where I have E $, so the follow set of, so a $sign can appear after an E. And then, you know, what else can happen? Well, where else can an E appear? Remember, we had that algorithm that looks at the right-hand sides of production rules. So here we have E followed by a $sign. Here we have E at the very end. And so we look at the follow set of this non-terminal and add it to the follow set of E, but this non-terminal happens to be E itself. So we should take, you know, the follow set of E and add it in here to the follow set of E, but the follow set of E is just $sign. So we just get $sign. So the follow set of E in this case is just $sign. And so now, you know, when do we reduce? Well, we reduce if the DFA would take us to a state that says you can reduce. So yes, okay. And if the next input symbol is in the follow set of E, right? So we're running the DFA on the stack only. So the DFA doesn't look at whether we have $sign or plus, but the $sign we match up with the follow set of E. Okay, and so if our input is a $sign, then the next input symbol is $sign. So it is in the follow set. So yes, we're supposed to reduce. If the next input symbol is plus, then you know, plus is not in the follow set. So we don't reduce. And here the symbol that we shift, right? So the symbol after the dot in the state, this symbol that is still going to take us to some state, some accepting state of the DFA or the NFA, is the plus, and that symbol is not in the follow set. So you know, when it's a plus, you shift, and when it's a $sign, you reduce. Okay, so in general, to eliminate the conflict, we look at that next input symbol, and if all the symbols that have shift transitions on them are not in the follow set, then you've eliminated the conflict, right? If you see one of the shifting symbols, you shift. If you see one of the symbols in the follow set, then you reduce. Okay, so so let me. So okay. So if you bear with me for another couple of minutes, I just want to summarize this. I also want to avoid erasing too much. So let me put it here. Okay. So if a DFA state contains A goes to gamma dot, so dot at the end, and B goes to alpha dot x beta, right? So dot not at the end. Then this would be a conflict in a shift reduce conflict in the LR0 parser. But here I'll add an extra condition, and x is in the follow set of A, right? So we would only reduce if that x is in the, if that next input symbol that's coming is in the follow set of A. So that extra condition, prevents the shift reduce conflict in some cases. So then that's a shift reduce conflict. Okay, and so the LR0 doesn't have the extra condition, and so it might have a conflict, but the SLR1 parser will have a conflict in fewer cases. Okay, and then similarly, if a DFA state contains A goes to gamma dot and B goes to, let's say, delta dot, then you'd have, normally you would have a shift reduce conflict, but now you only reduce by each rule if the next symbol is in their follow set. Is in the follow set. So if their follow sets overlap, then that's bad. So follow of A intersect follow of B is not empty, right? Then I have a reduce conflict. Okay, so at LR0 parser, it would get into a state that has these two reductions, and it wouldn't know which one to pick. An SLR1 parser is going to look at the next input symbol. If that symbol is in the follow set of A, it'll reduce by this rule. If that next input symbol is in the follow set of B, it'll reduce by this rule. And the conflict is only there if there's a symbol that's in both of these follow sets, because if that symbol comes up in the input, then the parser wouldn't know which one to pick. But as long as the follow sets are disjoint, again, the parser always knows which one to pick. Okay, and so in summary, our approximation of whether beta AA is a viable prefix, of whether we should reduce, is this one. So we use the LR0 DFA to check whether beta A is a viable prefix, and then the next input symbol has to be in the follow set of A. Okay, so that's the SLR parser. For the next lecture, we're going to look at option 2, so the LR1 parser. So there's going to be some grammars where this is not enough, right? Where the follow sets still overlap and where you still have conflicts. And so building the better DFA, the LR1 DFA, is sort of more powerful than the SLR1. But we're going to, use some of these concepts, like we're going to use the idea of following when we go to design that LR1 NFA. Okay, so I'm going to stop here. Are there questions about SLR1 for now, or questions about anything else? Then where should I stand? Okay, let's stand over here. Okay, so any questions? So I'll count to 5, and if there's no questions, I will end the lecture. So 1, 2, 3, 4, 5. Okay, so have a good couple of days, and I will see you on Wednesday for the next lecture, where we'll look at LR1 parsing.